uh, the cell lyses and releases thousands of virions into the environment, who then can infect the next tumor cell. So there are three major effects then of this infection. One is direct, where is this? Well, so there's a destruction of the tumor microenvironment, so it interferes with the microenvironment. It infects more tumor cells, and it also stimulates the immune response. So all of a sudden you have a viral infection there, and of course the immune response will come in. And there we get already the first problem. That is, if the immune response is too quick, then they come in and they clear out all the virus, and that's it. So we need to ensure in this treatment that the virus can reach all the tumor cells before the immune response comes in. Um, uh, like we heard in the previous talk, we need like a Goldilocks. So the timing needs to be just right. So the virus needs enough time to infect all the tumor cells before the immune response comes in and clears everything out. Okay. So there has been lots of mathematical modeling on oncolytic viruses. Maybe the first was by Helen Byrne, Kim and Wayne in 2001, but it really started around 2006 with the papers by Wodas, Dingley, and then Friedman and Tian wrote a long series of papers about this. More recently, Eftimi, Story, Poulat-Vand, Kim, Jenner. So there's lots of stuff, and I will, of course, use many of the results which have been derived previously. So here's the outline for today for the next 40 minutes. So I talk about a base model. So this is what it says. It's a base model, and then we do a quick qualitative analysis of this, which is really interesting. And then we try to use the model for reovirus. Reovirus is a very particular virus type, and we have a lab at the University of Alberta where they study reovirus, and so we work with them to try to optimize the effect of reovirus. Then I include the immune response because I said earlier that the immune response is very important. And then finally, I come to combination therapies of oncolytic virus and immunotherapies and see that maybe how they can be optimized as well. Okay. So here's a base model. So it's an ODE model. So in Christina's language, it's on the macroscopic level. We have cancer cells, we have infected cancer cells, and we have virus particles. So the cancer cells undergo logistic growth. It's a standard logistic growth term. They are infected by the virus. If they are infected, they become infected cancer cells. And these can die. They lyse with the rate alpha. When they die, we get new virions, which is this term alpha BI, where B is the burst size. So this means like maybe 1,000 new virions per death event. We also have loss term for the virus, which is just lost. And then we have this red term, which is virus loss due to infection, right? So if a virus binds to a cell, then the cell is infected and this virus is taken out of the virus compartment. However, I don't like this term. That's why it's in red. So the thing is, the virus particles are in the order, they're lots, they're 10 to the 9, 10 to the 10 virus particles around, whereas cancer cells are more like 10 to the 6 to 10 to the 8. So there's an order of magnitude between CI and V. And if one virus infects a cell, or maybe 10 viruses infect a cell, this is a minuscule term. This is a very, very small term here. And it should not make a difference in the virus particle equation. So what I propagate in my modeling, I just remove this. I get rid of this term and continue without. But before I do this, I want to show you the qualitative difference if we keep the term or if we don't keep the term. And this is, I think, here in the next slide. Not yet. Okay. First, I do a non-dimensionalization. So I get rid of a few parameters, right? And then theta, this will be the burst size, is my bifurcation parameter. Okay. So yeah. So then here, this is a bifurcation diagram where I use theta as a bifurcation parameter. And on the y-axis, go away, assistant. On the y-axis is the population of tumor cells. And 1 is the carrying capacity here. It's normalized to be 1. So for small burst size, the tumor just happily survives. And then at a certain value, around 5 or 6, you get a transcritical bifurcation, and the tumor size goes down, and we have a stable, steady state on this level. And then after a while, you get a Hopf bifurcation point right here. And then these are the minimum and maximum values of an oscillation. So you get periodic orbits, periodic solutions. Now, the red and the blue is with and without this term here, this kappa CV term. So if I take it out, I get the blue term. If I keep it in, I keep the red curve. So you see, qualitatively, there is a minimal difference between those. And this is my reason, my mathematical reason to get rid of the term. Biologically, I also think it is very small and can be removed. Okay. So yeah, let's simulate this. So I talked about a Hopf bifurcation. So let's see some oscillations. So here, theta is the bifurcation parameter increasing from 58 to 100 to 500. And then you see here the virus goes to 0, which is blue, and the cancer settles on a steady state. Here also you get a spiral into a steady state, and then here you get oscillations for higher values of theta. So now the question is, what actually do we want? Which of these cases is actually the good case for the patient outcome or for the cancer outcome? And what we see if we follow the red curves, okay, here the red curve really goes to 0 a lot. In particular in the beginning, right? It disappears under the blue, and then this repeats in these periods. So the periods seem to have a high amplitude, but they also go down to 0 to very, very low values. And so maybe this is what we want, right? The cancer is maybe so small that by random perturbations, we might actually lose it, and the patient gets cured. And there's an interesting framework which comes from stochastic modeling, which allows us to quantify the probability that the treatment is successful. And that's called the tumor control probability. And so I use a simple model, it's called the Poissonian model for the tumor control probability for these 3 images. Okay, and I think this is what I have on the next slides here. So the tumor control probability in the Poissonian framework is e to the minus C0s. C0 is the initial number of cancer cells, and S is the surviving fraction. Surviving fraction then would be the current tumor number divided by the initial tumor number. So we can plug it in from the previous simulations and we get these here, okay? And then you see in all pictures that the TCP raises to 1 here and here and here. And this is where we would like to be. So this means tumor control probability is 1. So it's a very high likelihood that the tumor is controlled or tumor goes extinct. In the periodic case here, we get these plateaus repeatedly on and on and on and on, whereas in the other case, we get it initially, but then if we are unlucky, then the tumor settles on a steady state right here. Okay. So it seems like the oscillations is a good case. It's a case where we want to be with our model. Next, we include space. So then the cancer, of course, occupies some space in the tissue, and we add diffusion terms here to the equations for the cancer cells, the infected cancer cells, and for the virus. And so what then happens is interesting too. So without diffusion, we can have oscillations, right? We have local oscillators. Now, if we couple them diffusively, we have spatially coupled oscillators. And spatially coupled oscillators can do any kind of things. There's the Kuramutu-Zabuchinsky model of coupled oscillators, and they can form spirals or rings or pattern formation or spiral waves or chaotic behavior or whatever. So it's really not clear what's going to happen if we add diffusion to the system. So let's look at this in 1D. So in 1D here, I look at 2 values. Theta is 58. This was the case where we have no oscillations. And 500 is a case where we have oscillations. And we initiate the cancer with 1 injection of the virus in the middle of the domain. And time goes down from 0 to 60. And so here's the cancer here, the infected cancer cells, here's the virus. And you see the infection with the virus spreads into the cancer domain. And then for low theta value, it just becomes a homogeneous equilibrium value for C and for I and for V. In the oscillatory case, though, yeah, everything is oscillating, and actually the oscillations synchronize. If I run this further, they become more and more horizontal. So it really synchronizes the oscillation, and then the entire domain oscillates in synchrony. Okay. So how does it look in 2D? No, this is not 2D. I want 2D. Here's 2D. So again, depending on the value of theta, we have different scenarios. But here we start with a low theta value, and what we get is if we initialize the virus infection here in the middle, we just get a ring which spreads out, a ring of infected cells, a ring of virus particles, and then this spreads out over the entire domain, infecting all the cancer cells. But if we run this longer, so here's again T is 1, T is 3. If we run this longer, this repeats. So T13 and 16, we get another inoculation in the middle, another ring. 24, 26, we get another ring. T34, 36, we get another ring. So it's kind of pulsing. We get a periodic orbits of rings, which then become concentric rings and are moving outwards. Another interesting thing here is we get a splitting in the middle. So this inoculation in the middle splits up into two. And we have no idea why this is the case. So this is robust in our numerics. It shows up all the time, but we don't know why. So I think it's an interesting question for further analysis. If we run this very long, so here we use 5 inoculations in the middle, so we get a deformed ring forming. But then over long times, 251, 600, 1,000, we get very chaotic patterns. And this goes on and on. This is not standing still. It is wobbling and mixing and rotating and going on and on. So we get very complex oscillations in this very basic oncolytic virus model. And this was published together with Abdullah in the Bulletin of Math Biology. And now my student Tejas is analyzing these patterns and trying to find spiral waves, if spiral waves are possible here. Okay. Yeah, so now we had this wonderful model and mathematical analysis and Hopf bifurcations, and we can do all these fancy patterns and so on. So I thought, hey, let's go to virology and tell them how all this works. So I approached Maya Schmulewitz. She is a professor in virology here at the University of Alberta, and she works on oncolytic viruses, in particular the reovirus. So then I made an appointment and I went to her and thought, yeah, okay, I have my super model, so we can explain everything. And of course, this totally failed. So she showed me the data, which I explain in a second. I tried to use my complex model and nothing worked. Absolutely nothing worked. So this is a nice story of how careful we have to be if we do modeling. So we had to rethink our modeling from the ground up. And I come to this in a second. But before, I like to tell the story about this plate here. So this is a typical experiment they run. They have petri dishes, and in these petri dishes live cancer cells, and they are colored in blue. So everything blue is cancer cells. And then they infect them with the virus, and the virus eats away on the cancer cells and forms these plaques, these little white dots here. These are the plaques for the virus infection of the cancer. And then depending on the concentration, you get more virus infection or you get less virus infection within, I think these experiments run 24 hours or 48 hours, something like this. So I made the appointment with Maya and I went to her office and I thought, okay, if I go to a virology lab, everything is highly secure and I get like a white coat and a mask and gloves and all that. But first I met her in her office and then she had this petri dish on her desk. And there was no lid on top. There was just this thing on her desk. And then she picked it up and held it under my nose. So this is a virus we are looking at. And I go like, gonna die instantly. So anyways, And she says, no, no, this is totally harmless for people. It's only made for cancer. Yeah, and I was not convinced. So anyways, um, so these are the experiments we're interested in to model. Okay. A little bit about the reovirus. The reovirus is a double-stranded DNA virus, which has a kind of a membrane thing here or capsids enclosing the DNA. There's a wild type which is called T3WT, which resides in the digestive tract of mammals. So most of us will have it in our guts. And this is also the reason why it's actually harmless to people. But it shows anti-tumor abilities and is now considered in over 30 clinical trials for metastatic breast cancer, prostate, colorectal cancer, and others. And there are even 2 phase 3 clinical trials on reovirus for breast cancer at the moment. So people put lots of hope into this. Now, preliminary studies show that only 21% of patients react or respond to the treatment, which means 79 do not respond. And this is not good enough, right? This is quite disappointing. So, so the question is, can we maybe enhance the oncolytic activity of the reovirus? Can we maybe make it bind better or diffuse faster or grow quicker? Or is there anything we can do to maybe find a better virus? And this is the question which Maya Shmulevitz in her lab is looking at. So they systematically develop mutations of the reovirus to increase the oncolytic potential. And they found a particular candidate which they call SV5. They call it supervirus 5 because it has 5 mutations. And this produces larger plugs. So it produces more white plugs in these experiments than the wild type. However, the binding rate of the supervisors is lower than the binding rate of the wild type. So it seems like a contradiction. So there is another virus which binds less but then makes larger plugs and makes larger infections. And this seems, well, at least at that time, that seemed quite counterintuitive to many people. So, and this is what we like to do. So is there something like an optimal binding rate? Maybe if we lower it more, then it becomes better, or is there an optimum? What should we aim for? Okay, so here are typical data that we have. So very detailed. This is then a microscopic picture of a part of the petri dish, and you can see individual pixels of infected cells and dead cells after day 2, day 3, day 4, etc. So these type of data are available. Now, so I said earlier that my super complicated model didn't work, so we had to model more simple. And we did this on 2 levels, a short time and a longer time. And short time, I mean, is the model on a level where the virus infection has not finished. So the virus infects a cell, and then it incubates in the cell for, let's say, 12 hours, 12 to 16 hours, and then the cell bursts. So, and the short time is 1 or 2 hours. So it's before the first viral infection could actually have happened, really. And so then we only have 2 processes. We have diffusion of the virus, which is here, and we have loss of the virus through binding to the cells. So we have a binding rate, gamma B, we have a diffusion term, and then we have just a very simple heat equation or diffusion equation for the virus with a loss term, which means we have 2 parameters to fit, a diffusion coefficient and a binding rate. And then based on the data which they have, we can do that. So for example, the virus was inoculated for 1 hour and then washed out from the cells, and bound virus was measured. And so we got a binding rate for the wild type of 61 and for the supervirus of 24 per hour. And so this is definitely larger than this value here. And so this is something we knew already as we started. Okay. Then for the diffusion coefficient, they made an extra experiment for us where they had this little tube just of medium. There are no cells in here. And they put the virus here at block number 1. and then measured the concentration of the virus in these compartments 2, 3, 4, 5, 6, 7, 8 over time. And then we get this here. And so then this is the solution of a heat equation. It's just a pure diffusion process which we can fit here. And I think I have this here. And then the diffusion coefficient becomes out to be 0.01 millimeter square per hour plus tolerance here. There are other ways in the literature how people measure the diffusion coefficient for virus particles, and I compare them here. So Rioja estimated 0.014, Poulard-Wand estimated 0.01, and you can use the Stokes-Einstein relation, and you get 0.02. So these are all in the same bulk part, right? They are more or less the same. Well, biologically, they are actually the same. And this is great. So then we have dV and we have the gamma as well. Okay. Now, this equation has an explicit solution. And then you can measure the T, the time, what is this? This is a spread radius. So you can measure something like a spread radius where the virus has kind of a minimum value. And beyond that, the virus is essentially washed out. And then here you see the spread radius depending on the binding rate. Okay. All right. So then model 2 would be on the longer time. So now we are interested in the virus replication cycle. So we let the virus infect the cell bursts, infects other cells, the other cells burst and infect more cells, etc. So then we model this by infected cells and by virus particles. And then the burst size comes in the theta parameter from before. So this is just a fraction of the model which I showed in the first part. So we get 3 more parameters. We get a percentage of the virus binding, which leads to an infection. We get a death rate of infected cells, which is A, and we have the burst size, which is theta. The dV and the gamma B have already been estimated now, so this is good. Now, Shmulewicz, they published in a different paper this percentage of virus binding that leads to an infection is about 1 in 100, so 0.01. So this is done. For the death rate, we have experiments, percentage of cell death over time. So we can, here we fit a logistic curve. We get A is 0.057. And for the release of new virions, we take the maximum value here, which is about 500 for the wild type and 700 for the supervirus. So these people are amazing. They do all kind of experiments which fit exactly what we need. So this is good. All right. So now we have, for this little model here, we have all the parameters here identified. So we would like to know how quickly does the virus spread over the cancer domain. So we do a traveling wave analysis. And just to remind you how this works, you take I and V at near a steady state, and then you do a leading edge analysis. So you assume you have X minus CT, which are the traveling wave coordinates. You have a decay rate lambda at the front of the wave, and you make an ansatz of this form, e to the minus lambda x minus CT. You sub it in, you linearize. Actually, this is already linearized. And then you get an equation between C, the speed, and the decay rate lambda. And then you find the minimum invasion speed. And so we did this, and we find for the wild type, we have a speed of 0.044, and for the supervirus of 0.059. So the supervirus is quicker. Although it binds less good, it seems to be quicker. And then here are simulations where this is done. And here lambda is a decay rate at the front of the wave for these 2 cases. So this gets to the root of the paradox a little bit, right? Even though supervirus binds less good, it does diffuse quicker over an entire cancer domain because it binds differently and it diffuses differently. Now, for the validation, we go back to take other experiments which we have not used so far. And from these experiments, we can measure the decay rate at the front of the wave, like here. So blue are the data and red is our traveling wave solution. And we can estimate the decay rates. And so measured, we get 9.8 and computed 6.9 or here 4.9 and 5.4. So this again, in biological terms, this is super close, and we call this then confirmed. Okay. All right. So I showed you a lot of experiments, but we forgot what is actually the question. The question was, is there an optimal binding rate? So can we even do better than the supervirus? And for this, we plot again, or we plot the invasion speeds. Okay. And so here are three curves. Let's look at the red curve first. The red curve is the wild type. The binding rate gamma B is here. And the speed, depending on the binding rate, is the red curve. And the wild type sits here at the red dot. So the red dot is the current binding rate of the wild type. And you see this red curve has an optimum here at the black point. So if we could reduce the binding rate of the wild type, we get to the black point and we get a faster invasion speed. Look at the top line, the purple. The purple is for the supervirus, and the supervirus has the maximum here, maximum spread rate, and the binding rate currently is here. So we can improve just a little bit if we move the binding rate to the right. So we want to increase the binding rate just a little bit to be better. And then we put a curve in the middle, which is kind of the average between the purple and the red. So here the burst size is 632, but then the maximum values are all very close together. Okay, so then to be more specific, we gave a table. This is what I gave to Maya Shmulevitz then. So if we have a burst size between 500, 600, 700 up to 1,000, and we have a binding rate of 0.28 to 0.5, then we get a speed of these values here and a plug size of this size. So then, these would be the optimal binding rates compared to the corresponding burst sizes, which give the corresponding plug sizes. And this is exactly what they want. So they can work on the binding rate, they can work on the burst size, and try to find some of these optimal values here. Okay. So Nurdan, you need to ask me you need to then tell me when the time is over. I think actually you are an amazing person of keeping time. That's
Yes,
fantastic.
yes, I'm definitely following the time. No worries.
Okay, so this is published then in this paper with Shmulevitz and Babtula. Okay. Yeah, so let's then maybe what do I have? I have maybe 10 minutes. Talk about the immune
Yes.
response.
Yes, you have 10 minutes.
Very good. So now we want to include the immune response. So all these experiments of Shmulevitz, they had no immune response, which is great. So we could focus on the basic virion infection cycle. But in the human body, we have immune response. So we add a Y equation for the immune response. And we model it very simply. So the immune response affects the cancer cells, infected cancer cells, and it also reduces the virus, all with different rates, P, Q, and S. It is stimulated by the cancer, which is this term. It is stimulated by the infected cancer cells here. And the the immune system is just washed out with the rate C. And it can diffuse as well. Okay, so now we have to do our mathematical hats on and remember what I said in the first 10 minutes, which was the black model here had oscillations, right? It has Hopf bifurcation, oscillations, and all that. The question is then, does this persist if I add the immune response? And it does. And I look at two bifurcations parameters now. So theta I used before, but then eta is a bifurcation parameter relating to the immune response. So this is how I can turn on or off the immune response. All right, so so we get 4 equilibria, which is a disease-free equilibrium, a cancer-only equilibrium where we have a 1 here. We have an immune-free equilibrium where there's no immune response, so this is 0. And then we have a no virus equilibrium, which is E3, and then we have a coexistence equilibrium E4. And then this is a combined bifurcation diagram, which was done by Negar Mohammad Nejad. So theta, the burst size, is on the x-axis, and eta, which talks about the immune strength, is on the y-axis. So if eta is 0, we are here at the bottom. And so along the x-axis, we see the previous bifurcation diagram. Here in red, the cancer persists. And then we get a transcritical bifurcation. In light blue, we have a coexistence steady state. And here at the dashed line, we have a Hopf bifurcation. And so the dark blue will be oscillations. Okay. Now, if you turn on the immune response, so making eta positive, we keep essentially the same picture for a while. However, if eta is too big, that's all the green area here, then the virus is lost. So if the immune response is strong, we lose the virus, and this green is entire dynamics between cancer and immune, and no more virus. Here in the dark blue, it's the opposite. So then the immune system is lost, and we have a dynamic between the cancer cells and the virus. And so only in this region, which is yellow and red, in the middle, we have a true interaction between immune response and virus infection. Okay, so if we want to gain anything between, let's say, an immunotherapy and an oncolytic virotherapy, we want to be in this region right here. So that's interesting. What is this? Okay, don't know what I did. Can I get rid of this thing? Oh my goodness. Yeah, okay. All right. So now we want to put this into the spatial context. I still don't know what I did. Annotate. Anyways,
sorry to interrupt. Maybe you can click on the arrow button on the left top. Maybe it works.
Okay, that seems to be better. Yeah. Yeah, thank you.
Sure.
Didn't even know that I can write on it. Okay. Spatial context. So this is the ODE bifurcation diagram, puts this in the spatial context. And then in this case, we look at traveling waves. Well, first of all, what we did, this blue area, we put this in visual PDE, 2-dimension. We also get the spiral waves and all that stuff. So this is very similar, persists. But analytically, it's easier to look at traveling waves. So we look at traveling waves first. And this is happening here. Now, so let's spend a minute to look at this graph. So we have cancer cells in orange. We have infected cancer cells in black, virus in blue, and immune system in green. Space goes from 0 to 60, population sizes on the y-axis. And then T is 20, 40, 60, and 80. So we definitely see traveling waves very clearly. But take a closer look. So here, this is the wave of the cancer, which invades into healthy tissue. It goes from here to here to here to here. But then here in blue and black, this is the viral infection. And the viral infection seems to be faster, right? It catches up with the cancer wave. And then actually it does catch up with the cancer wave and then moves at the same speed as the cancer growth. And this is then followed later by the green wave, which is the immune response, which follows and does not catch up. Okay, so it keeps its distance and actually looks even slower. Maybe it is even slower than the other one. So this is not one traveling wave, right? Usually one traveling wave is just a profile which moves around. What this is called stacked waves. These are stacked waves, so we have several components of the system which travel in different speeds. And it seems like the orange is slow, the blue-black is fast, and the green is slow again. So very curious. I'm in this business for more than 20 years, and I have never heard about stacked waves. I always thought traveling waves need to be one profile. But no, stacked waves have been reported, have been found in ecology, for example. And so we analyze those. And you can analyze these. For example, for the virus wave, you just linearize this steady state, or you do a leading edge analysis here. For the immune system, you do a leading edge analysis here. And for the cancer, you do a leading edge analysis here. So this indeed works. And these are the values we found. This is again together with Nigar Muhammadnejad. So the cancer invasion wave is 0.31. The virus invasion is 0.9, so much quicker. and the immune invasion into the virus is 0.33. So it's a little bit quicker than the cancer invasion itself, but definitely much slower than the viral invasion here. And then there's a fourth wave, which we do not see here, but which can be constructed as well, where the immune system invades into the virus, which is 0.304. Actually, no. Immune into virus is the one we see here. Immune into cancer is the one we are not seeing in these simulations. Okay. So yeah. Then my last section, maybe for another 2 or 3 minutes, how can oncolytic biotherapy further be improved? And in particular, collecting the immune response. And here are several ideas which we now have tested. So increase the burst size, optimize the scheduling, suppress the immune response, stimulate the immune response, combine OVT with CAR T-cell therapy. And then we also would like to look into PD-1, PD-L1 therapies, immune checkpoint inhibitors at a later point. Okay. And to do this, we test these ideas. For example, here we increase the burst size and look at the tumor control probability. And to remind you, we want to get TCP to be equal to 1. This is our good case. Everything else, 0.4 means 40% of cancers would be treated, and 0 is not good enough. Right, and you see increasing the burst size, if you can do this, you can get a better result on the tumor control, so which is nice. For the scheduling, I show you just quickly the simulations here. Now, these blue arrows are doses of oncolytic virus. And it turns out if we spread out the oncolytic virus treatments over 3 weeks or 4 weeks, we get a much better response in the tumor control probability. So it seems to be beneficial to spread it out over a longer time and do re-inoculation of the virus to get a very good result. Okay. So here's a heat map where we have day 1, we give the first dose of the oncolytic virus, and then we have week 1, week 2, week 3, week 4. And we indicate in color all treatments which lead to success. And the more yellow, the better it is. So the best outcomes are here on top, where treat on day 1 and then treat again on week 2 and treat again on week 3. But also week 4 treatments work really well. And I think this map is a really nice information for clinicians, where they now can maybe test different variations of scheduling to get better results. Okay. And then here's a summary of all these treatments. So increasing theta, only the highest value lead to success. So here's the maximum TCP. Green highlights all the good treatments. So for optimized schedules, we have a whole bunch of good treatments which you can look at. Including CAR T-cell therapy, we also have very good treatments where you get TCP equal to 1. So these are very promising approaches down here. Good. So I think this is enough. So let me summarize this a bit. The action of the immune response is central for the treatment outcome. Much can be gained through an optimized scheduling, and I think this has been largely ignored so far in this kind of study. People just do one inoculation and see what happens. But I think the scheduling can do a lot. Combination therapies are most promising for sure. And then mathematically, it's interesting. We can analyze spatial temporal patterns in these models, spiral waves, chaos. We can do a further analysis of the stacked waves. I don't know if you ever thought, no, you probably didn't. So stacked waves, you connect one steady state to the other with a traveling wave. So in phase space, this is a heteroclinic connection between steady states. Now, in my case, the phase space would be 8-dimensional, and I found at least 4 heteroclinic connections between different steady states. So it's like a heteroclinic tree in an 8-dimensional phase space. So good luck proving that this exists. And then finally, methods for treatment optimization need to be further developed, like we started doing with the optimization between the different weeks of treatment.